Derivatives of trigonometric functions, Level 2. Now that we know what the derivative of sine and cosine is equal to, we can go ahead and start figuring out the derivative of other trigonometric functions by using known differentiation rules. For example, we could find the derivative of the tangent function by using the limit definition of the derivative. But it is way easier to use the quotient rule together with the previous derivatives. Let's try this out by finding the derivative of tangent of x. We're going to do this by using the quotient identity for tangent. Tangent of x can be rewritten as sine of x over cosine of x. This way, we now have a quotient of functions. So we're going to take a derivative of the function by applying the quotient rule. Low d high minus high d low all over the square of what's below. So cosine of x times the derivative of sine of x minus sine of x times the derivative of cosine of x all over cosine square of x. We know that the derivative of sine of x is equal to cosine of x, and the derivative of cosine of x is equal to negative sine of x. Simplifying, we obtain cosine squared of x plus sine squared of x. We can replace this expression by using a Pythagorean identity. In this case, cosine squared of x plus sine squared of x is equal to 1. Finally, we use the reciprocal identity for cosine. The reciprocal of cosine of x is just equal to secant of x. In the end, the derivative of tangent of x is equal to secant squared of x. The derivatives of the remaining trigonometric functions, cosecant, secant, and cotangent, can also be found easily using the quotient rule. We summarize all the derivatives of trigonometric functions in the following table. You can also download a derivative equation sheet by visiting our website or clicking on the link in the description below. Remember that these derivatives are all valid only when x is measured in radians, so make sure your calculator is in radian mode. I recommend you gut memorize these trigonometric derivatives so that you can apply them quickly and not derive them every single time. Notice that the minus signs go with the derivatives of the co-functions, specifically cosine, cosecant, and cotangent. Alright, let's go over a couple of examples on how to apply the derivatives of trigonometric functions. Find the derivative of 3x squared times sine of x. For this problem, we have a product of two functions, in this case 3x squared and sine of x. We're going to apply the product rule for this one. Applying the product rule, we obtain 3x squared times the derivative of sine of x plus the derivative of 3x squared times sine of x. Taking the derivative of sine of x and 3x squared, we obtain the following. Since there are no like terms to combine, this is our final answer. Notice that all the differentiation rules still apply when working with trigonometric functions. Let's go over the next example. Find the derivative of r of theta equals cosecant of theta times the quantity theta plus cotangent of theta. Alright, for this function, we're going to make use of the product rule since we have a product of two separate functions, in this case, cosecant of theta and the quantity theta plus cotangent of theta. The first function would be cosecant of theta, and the second function will be the quantity theta plus cotangent of theta. Applying the product rule, which is equal to the first function times the derivative of the second function plus the second function times the derivative of the first function. Here, the derivative of theta plus cotangent of theta is equal to 1 minus cosecant squared of theta, and the derivative of cosecant of theta is equal to negative cosecant of theta times cotangent of theta. Next, we distribute cosecant of theta and distribute the negative cosecant of theta times cotangent of theta. Doing that and simplifying, we obtain the following. From here, we're going to factor out the cosecant of theta from all four terms. Next, we're going to make use of the Pythagorean identity. 1 plus cotangent squared of theta equals cosecant squared of theta. We replace cosecant squared of theta with 1 plus cotangent squared of theta. We then distribute the negative sign and simplify the expression by collecting like terms. We can then factor out a negative cotangent of theta from both terms, giving us the final answer. When it comes to the derivative of trigonometric functions, many of the answers can have multiple forms depending on the differentiation rule and trigonometric identity used. Let's go over an example where the derivative of the trigonometric function can be represented in two distinct forms. Differentiate the quantity 1 minus cosine of x over sine of x. Notice that the function is a quotient of two functions, so we can apply the quotient rule to find the derivative. Using sine of x as the low function, and the quantity 1 minus cosine of x as the high function, we go ahead and apply the quotient rule and differentiate the trigonometric functions. The numerator becomes sine squared of x, and distributing the negative cosine of x term, we end up with sine of x squared minus cosine of x plus cosine squared of x over sine squared of x. Next, we use the Pythagorean identity, sine squared of x plus cosine squared of x equals 1, to replace this expression. Doing that, we obtain the final answer, which is the quantity 1 minus cosine of x over sine squared of x. We can also find an alternative answer by using trigonometric identities before we differentiate. We could distribute sine of x initially to each of the terms in the numerator. Doing that, we obtain 1 over sine of x minus cosine of x over sine of x. The first fraction is equal to cosecant of x, and the second fraction is equal to cotangent of x. Next, we take a derivative of this alternative expression. The derivative of cosecant of x is equal to negative cosecant of x times cotangent of x, and the derivative of cotangent of x is equal to negative cosecant squared of x. Simplifying the expression, we obtain the following. We can also show that these two results are equivalent by using trigonometric identities. We distribute sine squared of x to each term in the numerator. Then we break apart the sine squared of x expression in the second fraction, and write it as 1 over sine of x times cosine of x over sine of x. Now, it is just a matter of replacing the terms with a trigonometric identity. The first fraction becomes cosecant squared of x, and the second fraction becomes cosecant of x, and the third fraction becomes cotangent of x, which is equivalent to the second form. Some derivatives of trigonometric functions may have patterns that can be used to predict higher derivatives. For example, if we are asked to find the 27th derivative of cosine of x, we can start by finding the first couple derivatives. In this case, the derivative of cosine of x is equal to negative sine of x, and then taking a derivative of this function, we get negative cosine of x. And then taking a derivative again, we obtain sine of x. The next derivative will be cosine of x, and the next derivative will be negative sine of x. We see that successive derivatives occur in a cycle of length 4. In particular, it is equal to cosine of x whenever the derivative is a multiple of 4. Therefore, the 24th derivative of x equals cosine of x. And differentiating 3 more times, we have the 27th derivative of x, which is equal to sine of x. So, we can use a pattern to determine higher derivatives. Trigonometric functions are often used in modeling real-world phenomenon. In particular, vibrations, waves, elastic motions, and other quantities that vary in a periodic manner can be described using trigonometric functions. Alright, in our next video, we will start going over the next differentiation rule, called the chain rule. If you enjoyed this video and you fortified your math knowledge, please like the video, share it with your friends, and if you're new, consider subscribing to the YouTube channel. If you want to remove ads from the videos, you can sign up to become a member over at our website, mathfortress.com. By becoming a member, you actively contribute to the sustained operation of Math Fortress and facilitate the ongoing development of additional content. Thanks for watching the video, and until next time.